discussion at the end of this. And the topic here is systems engineering for mission-driven modeling. Thanks everybody for tuning in. This is Peter Thornton at Oak Ridge National Laboratory, and I just want to start out by saying that this is not intended to be a criticism of anything that's going on in the E3SM project at the moment. In fact, I think you'll see by the end of this that it's quite the opposite, that it's in some ways a confirmation of a lot of what we're doing. But a little bit of additional background here. I've, just for various reasons for this project as well as other projects, been doing some exploration over the past, I guess, about year into what some high-level project management and engineering project design kinds of principles look like and guidelines look like. And part of that exploration has been to dig into what other big projects and other big agencies, especially mission-driven science agencies, are doing, and how they're approaching these kinds of problems, like the big complicated problem that we have in developing E3SM. So what I wanted to start with then is just to show you the big picture, which I don't think will be a surprise to anybody, but just to capture for the purpose of kind of framing where I think we are today with the E3SM project. And the top level point here is one that's been stressed from the very beginning of the project, that the couple science questions are intended to, and I would say largely do, drive the E3SM development. And then our strategic plan tries to capture those science questions as well as the top level requirements that emerge from those questions in more detail than just a couple of bullets about what the questions are. Currently, our project is decomposed according to the major science components and the supporting technology components, and there I would include things like the performance, the workflow team, the software engineering, the coupler team as supporting technology that connects the science components together and allows the science questions to be answered. Our component level road mapping exercises then have been used to describe what the new development would look like, and to guide the integration of new development components as directed by these top level science questions and discussions that went into the strategic planning. As we're all aware, the activity and progress across the project is being tracked at multiple levels, including in JIRA with the epics and tasks, as well as at the component level through various kinds of reporting, and at the system level through the usual kinds of development of the strategic plan and communication with our advisory board and communication to our sponsor. The current system actually, I think, does a really good job of implementing verification and validation. I'll have a little bit more to say about those two words later on, exactly what they mean, but we've got quite a sophisticated set of testing that's performed at multiple development and integration junctures that is intended to keep the project stable and robust. And finally, as design decisions are needed, they're being made on the basis of this kind of verification and validation testing and analysis of those results. So to me, this is kind of the summary of how things stand today. And as I dug into the literature and the background on how other projects are managed, I kind of came with an even bigger picture concept of how we might think about this project. And I think there's probably a lot of consensus in the project about how we view this. On this slide, I'm just focusing on kind of two potential framings for how you think about a big software development project like this. And because it's so much code development, and software testing, we could think of it in the context of other large-scale software development, like a Google or an app or Facebook, that kind of large-scale software engineering exercise. And I think in some ways it is like that. An alternative context that I think of this project more in these terms is as the model as a science instrument that's built to answer one or more research questions. And this is kind of a long-standing philosophy of mine in terms of how to guide model development in general, and I think it applies really well to the large-scale model development project that we have here. And just to give you some examples of what I mean by a science instrument, here are three, including us. The LIGO, that's making great headlines recently for actually observing gravitational waves. So this is an instrument, several instruments actually, and it's got a pretty clear mission: directly observe gravitational waves of cosmic origin. The Cassini probe is another example, and coming from NASA. Its mission to study Saturn, its rings, and its moons. Very simple, clear mission. E3SM, I think, is exactly analogous to these kinds of projects, both in terms of its scope and the science drivers behind it, and also I think the clarity of the mission. So this is pulled right from the BER E3SM mission statement on the website. So investigate challenges posed by interactions of weather, climate, scale variability with energy and related sectors. So very clear, concise. I like that. What I wanted to present next is just a little bit of background information that describes what I've been able to learn about how other agencies and other projects tackle this problem of how do you coordinate, integrate the activities within a large mission-based science project that has a large interdisciplinary team working on multiple components of a system that in the end has to all work together. And it's the system behavior in the end that's of the utmost importance, although all of the components need to be functioning properly in order to achieve that behavior. So in all of my exploration, the best examples that I've found so far in terms of laying out this concept in a way that is really accessible to lots of different kinds of projects is from NASA. And they, starting in about 1995, began down a path of really kind of codifying how they see these large-scale project developments in terms of formalized representation based on systems engineering. And there's actually experience that they developed starting with the Apollo missions, but they really hadn't codified it in such an exact way as they have now until the mid-90s. This idea of systems engineering goes back much further than that into the 1940s and Bell Labs and other research groups like that sure engaged in complex system development work that required large multidisciplinary teams and coordination of effort across those teams, as well as cultivation of creativity within those teams. And those are, I think, the two key elements that NASA has also captured really well in their documentation. Anyhow, there's this systems engineering handbook out there that you can download. I've actually got a hard copy of it that is a pretty nice paperweight. It's about 350 pages of stuff, and a lot of it is not really relevant for a generic interpretation of systems engineering, but about half of it is. A lot of it, connects to satellite missions and human space flight kinds of things, but quite a bit of it is actually really useful. And I'm I'm going to go through some examples that are pulled largely from that guidebook, that handbook. But I want to point out a couple things. One is that very similar methods and guiding principles are used at other agencies. And I've had a chance now to talk with people from NNSA and from the European Space Agency. And just in terms of reading, I know that this is also true at Department of Defense, that there is a kind of a standard methodology that's used across these multiple agencies for addressing the development, the design, implementation, operation, and finally kind of wrap up of these very large projects. So just to say a couple words then about what systems engineering is in the broadest terms, got a couple of definitions there, those first two bullets. The key points here are that this is a methodical approach that aims at design as well as implementation of design. It aims at technical management as well as operations of the final system or product, and then finally the retirement of the system. I don't have a lot to say here about the retirement, but I think it could be interesting to think about maybe later on. Another aspect of this is that NASA understands and captures this language too, that it's a science as well as an art. And so there is a considerable amount of creativity that is necessary to do this well. And that the approach is, although it might at first glance seem very restrictive and constraining in terms of the steps that are outlined, it's actually designed to be to have a number of different creative elements included in it, and concepts that allow for the expression of the creativity across a large team. So I like that about it too. And just to a little bit of nomenclature here, system in this systems engineering context is used to mean a construct or a collection of different elements that is essentially bigger than or more capable than the sum of its parts, which I think is an excellent paradigm for the kind of coupled Earth system model development that we're doing. So what I'd like to do then is walk through the steps in this systems engineering design process that I think I don't have time really in a half-hour presentation to think through or work through with the group the whole end-to-end process of design, implementation, operations, and closeout. But I just want to set that stage that bigger picture is out there, and then focus on the design part of it, and let you know that these other parts, the implementation and the operations component of a big mission like we have, are also described, and we can go into those kind of details later on if the group thinks that this is something that's interesting and useful to pursue. So here are the steps. I've laid out the kind of 9 steps. There are lots of different ways that the guidance in these handbooks can be sliced and diced, and I've kind of chosen the pathway through it that I think makes the most sense for our project. Those steps are to first identify stakeholders and the expectations that those stakeholders have, develop what could be called use cases, what NASA calls concept of operations, but which is really like a reference mission. This is a storyline that talks you through the operation of what you would actually do with this system once it was completed. And that's a very important piece actually in connecting the expectations of your stakeholders with very firm requirement statements. And that's the next step here, is to actually develop those statements, and they're formulated as this shall do something. So very simple kinds of declarative statements like that. We'll get into each of these steps in more detail as we go through, but I'll just walk through all of them quickly at first. Following on the definition of the requirements, it's important to connect measures of performance and effectiveness to those requirements. So you say the land model shall predict albedo within a certain percentage of observed values, plus or minus 10% of observed values. That's adding the measure of performance and a metric for success to the requirements. Then the next step is what's really the first very creative aspect of this system, which is the logical decomposition of the top-level system into component systems, and then the decomposition of that into further subcomponents. And this is called the system architecture, or there are various other nomenclatures for that. The purpose is to be able to allocate the requirements, which don't say anything about how to do something. They just say what needs to be done, what needs to be accomplished. This is now developing a system which can at least allocate those requirements down to a component that could be built or bought or reused or developed fresh, built on its own. At that point, still at that point, you haven't really done any implementation. You haven't, in our case, written any code, but you have an architecture that can capture at least all of the requirements that you've specified. Next step is to actually create, excuse me, and analyze alternative designs that meet the requirements and that fit within the system architecture that you've defined. And there can be multiple competing architectures. There can be multiple competing designs. And talk about this a little bit more later, but you're really only limited by budget and timeline schedules for how much creativity and diversity you can explore in those spaces. But at some point, you have to select the best design. And best, of course, is a loaded term here. You have to define what best means, and that reaches back to the measures of performance and effectiveness, and then validate and verify that that design is, in fact, meeting the requirements and that the system composed of all these components actually meets the stakeholder expectations. So that's one pass through this design process. And the point that I want to emphasize here is that, and this is, I think, a very critical point, that this process is not a once and you're done. This is a process which is both iterative and recursive. And what I mean by that is that it's iterative in that you can go through this whole process once and arrive at an initial system architecture, initial set of requirements, stakeholder expectations, an initial set of designs, and a simple implementation of a system. And you can learn something in that process and then go back and refine all of that. Go back to your stakeholders and say, this is what we've learned in our first pass. Does this have any impact on the expectations? Does that have any impact on our concept of operations? Does that impact requirements, and so on, all the way down through until you've refined the design to the point where you think it is ready to actually be implemented in a way that accomplishes the mission that you want to accomplish. The other part of that, as I said, is recursive. What that means is that you can apply this same process at each level of the system architecture. So you break down your system into multiple subcomponents, and you can apply this design, this design process down to the subcomponents as well. And again, the deeper you go and the more iterations you go through that, the more time consuming the process is, but also the more explicit and detailed the design is at the end of it. And probably it's true that the more confidence you have at the end of that process in the ability of the final design to actually do what you set out to do. So with that, I just wanted to go through a couple slides then about for each of these points what the some examples of how we fleshed that out for E3SM. So identifying the stakeholders. Here's a list that I just threw together of who our primary stakeholders are. It includes everybody from Congress and OMB down to us. We're stakeholders in our own process here as domain scientists and software engineers, but then other people as well, partner projects and agencies in the Earth system modeling community, maybe even the general public. I would hope so. Then in terms of identifying the expectations of those stakeholders, we have a lot to go on already. We have budget language and mission statements from the Office of Science. We have strategic plans at BER, the authorizing language for the project, our own proposals and feedback that we get from that, our own strategic plans, discussions that we have at various levels in the executive committee and group calls, our all hands meetings. And in the end, all this stuff should be documented really carefully and revisited frequently. So as you can see, so far, I think, we're doing what this process actually calls for in a pretty comprehensive way. So that's good. Development of concept of operations or use cases, the experiments that we've laid out, in the initial proposal, that we've talked about in the strategic plans since then, really serve, in my view, as these kind of design reference missions. They are the use cases. They are the concept that we have for how this system will operate. And the better developed we can have those early in the process, the better we can actually translate that into design requirements and eventual designs. This is a place where, of course, the whole team's creative input is required to get the right questions and to get the right concepts for how to answer those questions. The requirements, the requirements statements, this is maybe something that we don't do as explicitly as some of these other, guidance documents would suggest is useful. And partly we do some of it, but I would say that in terms of assigning requirements very explicitly and taking them from high levels down to very fine levels and refining those requirements in an iterative process and a recursive process, maybe we don't do that quite so much, and that could be something that would be helpful. Just to point out, these requirement statements are intended to say what the system does, not how it will do it. So you're not saying use this algorithm to solve this problem. It's saying the system is intended to solve this problem. And then the next step in terms of design, coming up with a design solution, is to figure out how do you actually solve that problem in the best way with the least cost. So defining measures of performance and effectiveness, I think we do a reasonably good job with that. We have lots of different metrics at different levels in the system that we're currently implementing. These requirements ought to be as quantitative as we can make them, and they shouldn't be any more restrictive than is necessary. And that's an art, right? You don't want to work yourself into a corner by saying you need to have 5 simulated years per day, or 2 simulated years per day, or 1 simulated year per day, or whatever the number is. You want it to be a reasonable number that's actually feasible to meet. And of course, this is the iterative process again. You might have to cycle back through and say, well, we have to change our expectations as a result of where we are currently with our design and technology. There's a couple of other examples here for what those requirement statements with metrics of success might look like. Then the logical decomposition and system architecture, as I said, is one place where we can begin to engage a lot of creativity in addition to the use case development that I mentioned earlier. So I'm just taking now, you already know the example for the whole system where we have a coupler and all of the components attached to that. That is one very cogent level of system architecture. And this is just taking that down to an additional level of work that we've done with the land group to identify different subcomponents of the land model and then subcomponents of those subcomponents. And by doing this, we have the opportunity to explore creatively what the system architecture space looks like, and we can have multiple competing visions for what this looks like. And we can pursue those visions as well to a certain point until we have to make some decisions about how to move forward for the next iteration. One example that I've spent a little bit of time thinking about and talking with Jennifer Holm a little bit is just when you take Fates as an example. It has the very sophisticated capabilities for canopy integration. We're at a point now where there's lots of new development that can be done with Fates, and so you can build that out and design a process or implement a process for getting to that next level of design that takes advantage of this paradigm, and it might be a useful way to go. The same thing could be said for the P-Flowtran development on the land model, or a lot of other aspects of the model development that we have going on. Finally, then, that's all still just conceptual in some ways, laying out how this system could be architected to meet the requirements. Then you have the problem of actually creating a design and analyzing alternative designs that can meet those requirements and fits into that system architecture. So, as I said before, the more detailed the requirements are, the better they can be flowed down to these lower level system architecture components, and then come up with designs that meet those requirements. This, to me, a really critical part of this is that those requirements can include interface designs that allow you to capture how different components connect with each other across that architecture, even across different levels of that architecture. And again, we should, and the experts say, do as much of this as you can afford, as constrained by schedule and budget. And also, as you're going through your second and third iterations, you've already done previous trade-off studies about what's working well, what isn't, what do you think your best designs are, and so you could be constrained by that. Finally, selecting the best design is a very challenging part of the process, but a necessary one. And there's actually a lot written about how do you engage multiple teams who have sort of vested interest after some time in particular designs, and come up with a selection of a best design. I'm not going to go into the details here because we don't have time to do it, but I'll just point out that there is sort of a paradigm here for if we look at cost on the x-axis and effectiveness, a measure of effectiveness on the y-axis. All the possible designs are kind of in the lower right-hand side of this diagram, and you want to have the most effectiveness for a given cost or the least cost for a given effectiveness. There's different ways to look at that. Finally, verifying and validating this design is done at every level of the system architecture if you're doing it well. And verification just means that you've met the requirements, but validation is more important, and it shows that the product that you've built at each level, whether that's an integrated product or sort of a lowest level product, that it accomplishes the intended purpose. In other words, it meets the stakeholder expectations. If you're verified but not validated, that means that your requirements aren't good or they're not complete. And so you either have to go back and refine your expectations, or you have to get more complete requirements. And so that leads into another iteration of this design process and learning lessons each step along the way. So I've said earlier that this was just one piece of a longer process, and so I'm not going to belabor that. The implementation, performance of the mission, and mission closeout are all equally interesting, and just don't have time to talk about those right now. And I'll just close with this summary that, in my view, E3SM is actually following many of these guiding principles of systems engineering already, and that's good. I think we're on the right track for that. I think we as a group could communicate our approach more effectively, both to ourselves as well as to our stakeholders, including like a review panel, if we adopted some of the existing guidelines more explicitly to say, hey, we're learning from this wealth of knowledge that's out there in the community already, and adopting some of those practices explicitly. And we might be able to increase our efficiency and improve the product by being a little more intentional about some of those steps, and I've listed them here. Documentation of expectations, the concept of operations and the requirements, I think we can do better there. Attention to this whole system architecture and actually iterating and examining multiple architectures. And finally, this adoption of the idea that you iterate on the designs before you move on to the implementation. So that's all. Thanks very much, and I'm happy to entertain questions.
Thanks, Peter. This is Andy Salinger. Yeah, and of course, I really like this. The one question I had near the end was the verification and validation. That occurring after selecting the best designs, you think the verification should happen the whole time you're doing work, and then the other part is the validation seems to be very similar to describing performance metrics.
Yeah, I should have mentioned, I'm sorry, Andy, that you and I discussed this and presented a poster on it at the previous All Hands meeting. I didn't have a chance to connect with you before this presentation, but just so everybody knows, Andy had an important role in helping make these ideas from the beginning. Yeah, it's true that I think the iterative nature of this process captures the issues with exactly how you time each of those steps, because you can go through one phase of it at a high level pretty quickly, and then you do have some verification and validation that's happening before your next level design selection process. Does that make sense?
Yeah, and then is there different in our case between meeting our performance measurements, like the ENSO, showing an ENSO of the right variability and amplitude? Is that the same as validation, or does validation go beyond meeting those performance?
I think validation is meeting those requirements, and then verification. I'm sorry, I've got that backwards. The verification is meeting those requirements, but validation is actually going on to be able to answer our big science questions. So, are we able to use this system to say something about the water cycle, or say something about the cryosphere, or say something about biogeochemical cycles? Those are broader questions and not very amenable to the kind of restrictive requirement statement.
Yeah. Okay. Well, thanks.
Sure.
Yeah, Peter, this is Phil. I guess what you said a little bit later kind of gets at this, but I think what you describe here on the software side is often kind of fits in that a waterfall model or a capability maturity model, which people don't use very much anymore, in part because you often get stuck in these boxes and kind of gold plate the requirements, and you sort of get stuck there for a long time. Whereas a more agile process where the iterative nature of this happens on a very fast time scale kind of gets closer to what we actually need on the software side. So I think, you still have to kind of go through some of these steps, but I guess the point is you need to move through them pretty fast and not get stuck there.
Yeah, that's a really great point that I've dug into. The agile versus systems engineering. How compatible are they with each other? And I understand what you're saying, and I'm actually not sure if there's maybe a hybrid approach of this that would be the best solution for a mission like ours, which has a big science driver, but also a huge software development component. In some ways, I don't think that the issue that you raise about what the things that Agile solves for a software project are probably not very different than developing a circuit board, right? I'm not sure that they're very different.
Yeah, I think, I mean, part of the point is you want to get some rapid prototyping done, because often you don't know what the requirements really should be. So you start out with a set of requirements and they often change when you start to implement. So you do need that feedback process.
Yeah. Yeah. And I guess that's the iterative part of that I was trying to emphasize, is that you want to go through this quickly once, and then a little more slowly another time, and recursive, meaning that you can be iterating at various levels in your hierarchy once you have a hierarchy. So it sort of builds itself out as you move that way. Yeah, I guess I'm curious whether people think that this could be useful in terms of how we present our approach to our sponsors and reviewers.
Yeah, this is Dave, Peter. First, I got to say, Ricky Rue would be proud, right? He's been pushing the NASA approach for years and years and years and years.
Oh yeah.
And so and I think it is good to do, but we have to realize that a lot of these things, it's a very engineering approach, which has resonated with, like you said, a lot of what we do. But some of what we do is not engineering, and the research process itself doesn't lend itself very well to some of these engineering approaches with very strictly defined requirements. So it makes it interesting.
Yeah. I mean, I think a NASA satellite mission has the same problem, right? It's a research problem, trying to understand the moons of Saturn. But there's a lot of engineering that goes into making that work.
Right. But I think the engineering part is what we do, which is still at least 3/4 of the project should follow this approach. I agree with you. So anyway, well, it's 9:10 here and 12:10 back there. So probably a good thing if you got any further questions, take them offline with Peter. And thanks for doing that. I appreciate it.
Yeah, my pleasure. Thank you.
Okay.
Bye-bye.
Bye, everyone.